Hi everyone, Mr. Smith here, and in this video lesson, we're going to talk about electric potential. So it might be a heavy one, so be warned, one of our heavier lessons. This idea of electric potential takes a bit to wrap your mind around. It's a little theoretical, but we'll get through it. It'll be okay. Let's get started. So let's kind of recall what we've done for gravitational forces, right? So for gravitational force, we had EG, that should be FG. That was our starting point. FG was G, M1, M2 over R squared. And from that definition, we did a derivation, if you recall, for gravitational potential energy, an updated version of that. We said that an updated version of our gravitational potential energy was EG equals negative G M1 M2 over R. And it was negative because it took negative work to bring objects together. From R equals infinity. Why negative work? Well, because two masses, they attract each other. And so they would naturally come together. You don't actually have to do anything to bring them together. In fact, as two objects come together gravitationally, you actually lose energy. So that's why this gravitational potential energy is negative. It's when you separate objects that you gain potential energy. So we got this expression for gravitational potential energy, and it was always negative because we always lost energy as two objects came closer together. But what we've seen from our last day is that the electric force was actually very similar to gravitational force, K, Q1, Q2 over R squared. And this gave us, remember, this gave us the magnitude of the force. But here's where we're actually going to make use of signs when we talk about Q1 and Q2. You can do a similar derivation to show that electric potential energy, the work required to bring two charged particles together from R equals infinity, is given by K, Q1, Q2 over R. And I'm going to add a little note here because this is kind of the first time where it actually matters in our equations. The signs matter on Q. So the shape, the structure of the formula comes from the exact same derivation we've already done. But let's talk about the signs. Why no negative? Well, if we think about what were to happen, if I were to plug in a positive charge and a negative charge, those two things would attract each other. And if one Q is negative and one Q is positive, I'm going to get a negative electric potential energy, just like gravity, because two oppositely charged particles are going to attract, and it's the exact same case. However, let's say Q1 and Q2 are positive, they're the same sign. Then in that case, they want to repel, and you actually have to do work to bring them together from far away. So you want a positive value for EE. And if both charges are negative, note you also get a positive electric potential energy, because two negative charges, same thing, they want to repel. And so you'd have to work to bring them together. So this very natural extension for electric potential energy, we're not going to rederive it. And note the signs. The signs matter because with electric potential energy, sometimes it takes work to bring charges together if they're the same charge. Other times it doesn't because they're attracting each other. All right, so I think I need to write this in. Yes, I do. Electric potential energy. The potential energy stored. This is the potential energy stored in two charges are meters apart. And you can see we have two curves showing you the equation. So the bottom one is the one that is similar to gravitational potential energy that was always negative. And that's the case when you have attraction going on. Q1 and Q2 are opposite signs, so they want to attract just like gravity. And the reflected curve up top is what happens when things are repelling. In that case, the electric potential energy is always positive because it takes work to bring things together. And when you separate things, you store energy. I have a couple of notes to add for this one. So I think we've hit this one already a few times. It can be positive or negative. So I think I've made that clear. Don't need to write anything more than that. And my second note, I just want to emphasize this. So the electric potential energy, you can think of it as the energy stored in two charges are meters apart. So as you bring two objects together that want to repel each other, right? It's like almost like compressing a spring. You're storing energy, and then when you release that, they're going to fly apart. But you can also think of this as the energy required two charges together from r equals infinity. And in a case like that, the work required gives you this electric potential energy. All right, so we've established the formula, and we've talked about how it can be positive or negative, which makes sense because we need one case for attractive, one for negative, and the signs matter. So when we're talking about potential energy and potential, we've got to keep in mind the signs. So what often happens, though, so say you have some big charge Q setting up an electric field. And you put, say, Q1 there, and it has, Q1 and big Q have a certain electric potential energy. And, but let's instead say of Q1, maybe you put a second charge there with a different charge and it has a different potential energy. And then you put a third charge there and it's going to have another different potential energy. So instead of, having to do the potential energy for all these different cases, there's this concept where we just look at the potential energy per unit of charge. And this is called electric potential. So it's electric potential energy divided by per unit of positive charge. So the derivation looks like this. So it's very similar to electric potential energy. So electric potential, or voltage, V, is just electric potential energy divided by basically divided by a positive test charge set up in the field. What does this look like? Well, the electric potential energy stored between some big charge Q setting up a field and some little charge Q in the field. We already just calculated that. It was K big Q little q divided by R. But instead of having to do this calculation for a whole bunch of little q's, if you divide by the unit of charge, or divide by the charge on the smaller guy, you get this. You get K big Q over R. And so you have just one potential in the field for a charge setting up the field. So actually makes a lot of things easier, allows us to look at electric potential energy in a systematic way instead of always having to worry about, well, what if it was this charge or this charge or this charge? We have a charge setting up the field, and the voltage is this, and it kind of gives a generalized electric potential energy. So we'll do some we're going to do some calculations in a few minutes. And every time we do a calculation and get an answer, we'll just kind of talk about what that means. So you'll notice that this voltage, this electric potential, it's energy divided by charge. So the units are joules per coulomb. And we call that the volt. So in your grade 11 course, when you look at circuits and you looked at V equals IR and all that good stuff, you were using electric potential. But we're just kind of revisiting that and kind of driving that from a more basic place. This gives us a definition of the volt. Now, I don't have any specific spot on your lesson sheet for this, so maybe you want to jot this down somewhere. But 1 volt is the electric potential at a point in an electric field if 1 joule of work is required to move 1 coulomb of charge from infinity to that point. So it gives us just an idea of what the volt is. So let's just do a simple example. We're going to calculate the electric potential 0.4 meters away from some spherical charge setting up a field. So voltage, K, Q over R, 9 times 10 to the 9, K. Our charge, positive 6.4 times 10 to the minus 6. Again, sign is important here when we talk about potential energy and potential. And R, 0.4. So let's calculate this, and then we'll get our answer. It will be in volts. And we'll actually talk about what this answer means. Times 6.4 negative 6. Okay, 144,000 volts or joules per coulomb. So what this means, I think about it this way. So this is just a way to interpret our answer. It would take 144,000 joules of energy to move a 1 coulomb charge here. So that's just a general way of saying the potential energy at a point, but it's independent of the charge in the field. So 1 coulomb charge would take 144,000 joules. A 2 coulomb charge, it would take 288,000 joules. You just take the voltage and you multiply it by the charge. So this general potential, this general electric potential, can actually be a lot more useful than electric potential energy. Even if we're just, we're used to this energy, conservation of energy, and working with something different can be a little confusing at times. It really can be useful just thinking about terms and things of what's setting up the field. You'll just have to trust me on that one. Yeah, like a 0.1 coulomb charge would be 14,400. So again, it's just a general, giving you the general electric potential in the field per unit of charge. So in all the definitions, we've been talking about, hey, this is 144,000 joules of energy to move a 1 coulomb charge here, but it's been from like R equals infinity, so from very far away. But other times, we just want to know the difference in energy or the difference in electric potential from one point to another, like say across 2 parallel plates or across a circuit or over the resistor in a circuit. So in those cases, we're talking about not electric potential, but we're talking about the difference in potential between 2 points, electric potential difference. So look at that in a second. Now, I don't believe I have a spot on the lesson sheet for this as well, but if you have multiple point charges, so we just did an example for some charge Q. And we found the potential at a point in the field by doing potential is just K, Q over R. But what if you had multiple point charges? Because we've seen like a lot of scenarios where you might have a positive, you might have an electric dipole or just a lot of charges in the field. So what would happen if, say, I threw in a second charge here and say that was Q1 and that was Q2, and is at a different distance, R1, R2. So how do you find electric potential energy and electric potential for multiple point charges? Well, it's actually pretty straightforward. You just find the individual potentials and add them together. So you just do KQ1 over R1 plus KQ2 over R2. And then you just, as many point charges as you have, you just can add those voltages together. And it's the same thing with electric potential energy. If you wanted to know, hey, what's the electric potential energy if I got a little charge Q in there? Well, you just find the electric potential energy, don't need the Q1 there, between the first two guys, and then you find the electric potential energy between the other two guys, and then you add them together. So for multiple point charges, you just add. It's not overly complicated, and these aren't vectors; these are scalars, right? So these just give you numbers that you can add together. So it's actually not that bad to do multiple point charges. Just find the individual energies or potential and add them together. So a little bit of an aside. That's going to cover maybe some practice questions where you do multiple charges. But yeah, it's not that bad to handle. Just add them together. All right, so we're going to derive some equations involving electric potential difference. So if you can imagine, you have an electric field set up and you want to move some charge from A to B. Well, it's going to take some work, especially if this Q is a positive test charge, again, which it always is, and you can see the field lines pointing right. So remember that this is the field lines point in the direction that a positive test charge would want to accelerate if it was at rest. You drop it in, that's the way it would move. So it's going to have to take work to move from point A to B. But the idea is that it doesn't matter whether you go straight from A to B or you do a winding curve from A to B. The electric potential energy difference, the change in potential energy and the change in potential, it's the same. It's exactly the same as lifting something up in the air. So if I take my tablet pen here and I lift it up, I've stored some energy in that pen, right? But if I lift it up in a zigzaggy pattern, the change in potential energy is the same. It doesn't matter the way I got there. So that's what that diagram indicates. So like gravitational potential energy, I'm just going to say the change in electric potential energy is independent of the path. From A to B. So I hope that reasoning made sense. Again, it doesn't matter whether you go straight there or whether you take a zigzag pattern. The change is the same. You wind up at the same spot. Right, and we're going to get an equation for this. So an equation that ties in potential difference. So let's talk about the work. Required. And we're going to talk about the work per unit charge moving that charge Q from A to B. So we're going to get an expression for well, first of all, the work required to move it there is the change in electric potential energy. That's the work. You do the work pushing the charged particle from A to B, you're going to store some energy, right? So that work goes to a change in energy, but potential difference remember, potential is potential energy per unit charge. So the work required per unit charge, we'll divide that by Q. And this gives us what we call potential difference. And sometimes we rearrange this equation to get change in electric potential energy. It's the potential difference times Q, times whatever you're trying to move across that potential difference to get the change in energy. It's a pretty easy calculation. You take the charge, E times the potential difference. Just another variation of this that we may use, that potential difference is the work required divided by Q. Again, that's just this version here with work substituted in for delta EE. So at various times, any one of these will be maybe useful, but when we get to parallel plates, this guy here is going to be useful for us. But yeah, so nothing crazy big. It's electric potential difference. It's just the change in potential energy divided by the unit of test charge. So let's do calculation, interpret what we get for our answer. So how much work must be done to increase the potential by 120 volts? So we're talking about, again, what we're talking about here is, so we've got some potential difference. We've got some electric field we're in. And we've got this charge, QT, from point A, and we want it to move it to point B. And we're told that across that, there's a potential difference of 120 volts. And we've got the size of the charge, so we can find what the work done. So the work done is equal to the change in electric potential energy, which we now have a formula for. It's Q times delta V. And so here we have, and signs matter with energy and potential. So we have 3 times 10 to the minus 7. And the potential difference, 120 volts. Again, that's joules per coulomb. So when we use volts and coulombs, we're going to get out energy. We're going to get out joules as our final unit. So that is 3.6 times 10 to the minus 5. I think it's 10 to the minus 5. Yes. So what does this mean? It takes 3.6 times 10 to the minus 5 joules of energy to move a 3 times 10 to the minus 7 coulomb charge from A to B, where that distance from A to B, there's a potential difference of 120 volts. So again, every time we're right now doing a simple calculation, just trying to wrap our minds around what that means. So you can see why potential, like I can see why potential is useful, because so here we required a certain amount of work for this charge, and for another charge we'll need another amount of work, and another charge for another amount of work. This 120 volts just summarizes all that just in one kind of statistic. All right, let's continue. So we talked about how potential applies and electric potential energy works for point charges. But as we've seen, things are a bit different for parallel plates, because our derivation for electric potential energy, if I go backwards, this derivation here, we have this equation. That was true for point charges, where the force changes depending on where you are, right? The force is dependent on R. But remember, in a parallel plate, the electric field is constant, and so the force is constant. So we need to handle this. We need to talk about how to handle electric potential and electric potential energy with parallel plates. So if we look at a parallel plate, and you can see the field lines pointing to the right, and you should be able to think about, well, which plate is positively charged, which is negatively charged, based on which way the field lines are going, right? This guy is a positive, and this guy's a negative, because a positive test charge, and we have Q here, is always going to be moving from if we just let it go, it would be moving from the positive plate to the negative plate. So that's why that Fe, the electric force shown on here, is moving right because Q is going to be attracted to the negative plate and repelled from the positive plate. And we're going to ask, so we're going to look at the work we're going to need to move that charge Q from the negative plate to the positive plate from a region of low potential to high potential across a certain potential difference. And the force is constant and the distance is r. Well, if you recall back from grade 11, you guys actually had an equation for work that involves the constant force being applied and the distance, right? So that's our starting point. So the work required to move that test charge across a potential difference from low potential, negative, to high potential, positive, it's going to take some work, and it's going to be equal to our the force times distance, which in our diagram there is r. And then the angle between them, the angle between the force and where it's moving, they're actually parallel, right? So the angle between them is 0 degrees. So work equals F times R. And I want to add a little note too. And actually, let's just do this first. So work equals F times R. Remember, just like Fg equals mg, force equals Q times epsilon, right? And since E is constant, F is constant. Got to stress that. Inside parallel plates, the electric field is constant, the electric force is constant. So we have this expression, the work required to bring a charge Q across parallel plates of that are separated by R that generates an electric field, epsilon, is this. It's Q times epsilon times R. But we just actually found another way to get work involving electric potential. So also, we just derived this expression. The work required is the change in potential energy. So it's going to take work to move that charge. All that work goes into storing energy, so changing the electric potential energy. And we just talked about that that's equal to Q times delta V. Well, so we have two expressions for work. They are equivalent. We can set them equal. So Q delta V equals Q epsilon R, and then we get an expression for delta V, independent of the charge in between the parallel plates. So that's pretty cool. So what this equation tells us is that the change in potential is proportional to R. So, and this kind of makes sense, right? So let's say that from moving my tablet pen from here up to here stores a certain amount of gravitational potential energy. What fraction of potential energy am I storing if I only move it halfway? Well, it's half, right? So it's the same with electric potential. As you go across two parallel plates, so I'll do it like the diagram. So if I move a charge, and it doesn't matter what the sign of the charge is, if I move it all the way across the plates, I have a certain change in electric potential. And if I move it just halfway, it's half the potential. So keep that in mind. I'll leave it, maybe add a little note on that. If you go halfway from A to B, A to B, the potential difference would be halved. So it's just like gravitational potential energy. All right, let's just do a couple examples. Numerically, these are pretty easy. This might have a little quick chat about what the answer means. So we have a uniform electric field. So when you see uniform electric field, you're thinking capacitor or parallel plates, right? And in the same way, when you read parallel plate, you're thinking uniform electric field. So that we have the potential difference. It's 150 volts, and the plate separation is 12 centimeters. We're going to determine the magnitude of the electric field strength. So it's like we've got two parallel plates. Oh, my drawing is terrible today. Plus. So two parallel plates. We're told that the potential difference between them is 150 volts. We're told that those plates are 0.12 meters apart, and we're asked to find what the magnitude of that electric field. Now, I almost drew the field lines in the wrong direction. What direction would the field lines be in the way I draw my parallel plates? A positive test charge would move away from the positive plate towards the negative plate. So that's the direction of the field, but we're not asked for that. We're just here to find the field strength. And it's actually really easy because those three things are related by delta V equals epsilon times R. Epsilon equals delta V over R. And we get, so 150 divided by 0.12. 1,250, and the units newtons per coulomb. So if you guys could imagine a 1 coulomb charge on the negative plate, it would take 1,250 Newton force to, a 1 coulomb charge in that electric field would experience 1,250 newtons of force. That's quite a lot. So that's just playing around with that equation. Let's do a second example. So here we have the field strength. We have the plates connected to a battery, which makes a charge on each one. And that potential difference is 95 volts. What's the plate separation? So again, pretty relaxed question, just playing with the formula. Delta V equals epsilon times R. Here we're finding the plate separation. That's R. So delta V divided by epsilon. 95 divided by 450. So again, we're in newtons, we're in coulombs, volts is joules per coulomb. And so we know with SI units, everything's going to pop out. And well, at least in this case, finding R, it's going to pop out in meters. And so we get about 0.21 meters, so 21 centimeters. All right. We've done a lot of heavy lifting here, and that's going to allow us to analyze some pretty cool things. And I can tell you that having done the heavy lifting, the hard part's over, and we just get to apply. Specifically, we're going to look at some parallel plate stuff where this idea is going to be really helpful to us. But yeah, the heavy lifting is done. What I usually like to do, because some of these concepts can be so kind of abstract, I like to do a little summary. So if you'd like to get these copied out, you can. I've just had positive feedback when I've done this teaching the class face-to-face. So the first thing we learned with electric forces was electric force. And I think most people didn't have a problem with that. This equation gives us the magnitude of electric force between two charges. And it was just, remember, it was the magnitude. So when we're doing force, we don't plug in the signs, right? But yeah, I think most people have, yeah, that makes sense. It's just like gravity, right? And then we talked about electric field strength. And most people, at least in my experience, are like, okay, I can buy that because it's like little g equals big G, big M over R squared. So it was a parallel to gravitational fields. And in my experience, most students were like, okay, yeah, field strength, gravitational, electric field strength, gravitational field strength, very similar. I can buy that. The units were newtons per coulomb. And a specific example, if you were to calculate a field strength or given a field strength of 100 newtons per coulomb, it means if you put a 1 coulomb charge there, they would experience a 100 Newton force at that spot. And again, in my experience, electric potential energy is generally well received too, because we've already derived gravitational potential energy. And I think it's a natural extension. And I think most of the time too, students are okay with it can be positive or negative, because charges can attract or repel. So it makes sense that we get two options. And this is the first case where the signs matter. So when we get to energy, you got to remember signs matter. All right. And then we get to potential. And this is where it becomes a little abstract for some, because they just can't wrap minds around, well, we already have electric potential energy. Why do I want to just do electric potential? I already have electric potential energy. But there is value to removing the specifics of having, like, we have some point charge setting up electric field. There is value in just eliminating the second charge and just talking about the potential in a general sense. Whether you believe that or not, that's okay. But there is value there. So the potential is the potential energy per unit of charge. So what happens if we get a voltage of 100 volts or 100 joules per coulomb? So this means it would take 100 joules of energy to bring a 1 coulomb charge in from infinity. And the signs matter here, can be positive or negative. So signs matter when you're calculating electric potential. And this is the equation for a point charge. And if you just imagine multiplying by a 1, well, then it's the electric potential energy for a 1 coulomb charge, right? Okay, and then we talked about electric potential difference, and it was the change in potential energy, or the work done, divided by the test charge Q. And it's just the potential difference for 2 point charges is KQ over R2 minus KQ over R1. So it's just voltage is the change in energy per unit charge. And if you have point charges, you just subtract those two. That was for point charges. So interpretation gives a change in potential between two positions. Potential difference for parallel plates was different because the force in the field are uniform. That makes things different. We can't use our point charge equations. So we derive this new equation, delta V equals epsilon times R. So the change in potential depends on the electric field and R. And remember, since since epsilon is constant, just like G is constant and E equals mgh, since epsilon is constant, the potential difference depends on R. So you double the plate separation, you double the potential difference. You have it, you have the potential difference. So this is the potential difference across a set of parallel plates, and potential difference is proportional to R since epsilon is constant. So it's my hope that summary table just makes things a little bit more palatable for you. Again, in my experience, most students are pretty cool up until electric potential energy. Everything's kind of gravy. And then electric potential is that one concept that is a little tough to wrap our minds around. So it's my hope that you guys found value in that summary table, and that you guys will do some practice. And it just takes practice. It takes thinking about what our answers mean in terms of energy and work to kind of become comfortable with voltage. So now that we've done the heavy lifting, we now can look at a relatively simple but very cool application of potential difference and look at how Robert Millikan determined the elementary charge, i.e. the charge on an electron or proton. It's so tiny. It's like 1.602, if memory serves me correctly, times 10 to the 19 coulombs. So how on earth could we measure a charge that precise? Well, we're going to talk about it in our next lesson. Until then, hope you're staying well. Have a great day, and we'll see you soon.